Okay, this should be working. A few more minutes and we'll get started.
Sweet snacks, John.
Just need a box of coffee in my office in the Instafence. So bring that.
Stuff I haven't done at all, so.
Maybe there's like cake in the box. Maybe cake that was shipped in.
What's in the box?
So,
We need
cool, man. It's cake from England.
awesome.
It's very bland, right?
Silicon Valley. Couldn't be a worse place, but
It's
the only place in the States that's hotter with
yeah. It's like a 400 square foot apartment room thing. Cost them $2,000. Poverty.
I mean, they got like record somewhere around there. They hit like record highs, like 140, something, right?
Yeah. I don't have to do that. It's hotter than Europe.
Joe fact.
I go there, I step out like this. Done.
Take your kids.
Yeah. It's understand more this go be a janitor.
Sure, right. So you're really cool.
For a few days. I thought everybody in the lab was like that.
You guys can't take data, are you?
We still take data.
If you fail.
You
Good red paper on detecting other people.
We can tell you with our atoms when people are doing construction over scale.
It's like the last time.
Before you look out the door.
And they're already.
Yeah.
Like
sometimes a second.
I'm like, what happened? Everything is different.
Genuinely surprised.
You look happier. It's like fuller, more healthy.
I meant to email you.
Totally different. Totally different. Wow. How's it going?
Yeah.
Like seem relaxed. It's very. I like fog it. PGP.
It's really fun when I pick up the stuff.
What? PGP? It's a financial.
Yeah, so yeah,
That's got bombs in the field. And we didn't touch on that. No. This happened in the Bengals preseason yesterday.
Oh, no.
He's like about to take the snap. Box air field takes the snap. There's I guess.
It's not.
He has a history of power on the field. But usually just like for operation. Yeah. See that pitcher get hit in the head last night. He was like crawling around and like tried to stand up. It was like clearly like had no idea like where he was on Earth. And then like Salto and Arke ran up to it. He's on the Marlins. I forget. The catcher ran up to him and he like collapsed. Yeah. Like his reaction after getting hit was like so bizarre. It's like it's perfect for all the
I hope they wouldn't hit. For the book, but like your
Oh, your head's bleeding?
It wasn't big.
It wasn't bleeding. Skull was bleeding. People don't know what's going on.
Temporarily.
The funds are used.
We're open to pitches you later.
Those are fun. Or maybe I'll stop by the time I do it.
Yeah. Weird when you know it's
No, it's good.
Is it on?
Yeah, I turned it on. No one's watching it yet.
Before the current configuration.
How's Emma playing a drinking game of this? Every time he
John, you want the door closed?
says a word.
Every time it says a word, we're waiting for
Charles.
Can you teach us about sine wave, Sean? Is that part of it? Or?
No.
Sounds good. There's no secret.
You can get my spot on the counter if you want, but
We can move one of these stairs around. You can see like right in the middle, this stair shoot.
At this desk.
Can you get the front set of light? Yeah, perfect. Thank you.
Good. So thanks everyone for coming. I'm surprised to see this big crowd given the semester hasn't started. So it looks like you all love the summer of Tucson. so good. So after years of work, so John tonight is going to tell us about some search for new physics apparatus.
Okay, great. Thanks, Shifang. And thank you all for coming to my defense. So the title of my dissertation is Searching for Supersymmetry at the Large Hadron Collider, Studies of Sleptons and Stops. Okay. So let's begin with an outline of what I'm going to talk about today. I'm first going to give a brief introduction about the standard model, about the particle content and the interactions, how the particles interact together. And then very quickly we'll move on to go beyond the standard model, and we'll talk about the minimal extension using supersymmetry, which is called the MSSM. And I'll highlight regions of interest where we want to search for supersymmetry at the LHC. In particular, we're looking for Sleptons, which are the superpartners to the leptons, and stops, which are superpartners to the top group. And we'll look for Sleptons in two ways, either by producing them through cascade decay, or by just looking at them through pair production with a few modifications of the what's called the LSP, the light supersymmetric particle, the character of that. And then I'll conclude. So the standard model, it's extremely successful theory, explains all the fundamental interactions, well, three of them. We have the strong force, which is responsible for gluing quarks together. We have the electromagnetic force, which is something we're all familiar with, in charge of electricity and magnetism. And we have the weak force, which is responsible for radioactive decay. So we do know that there's a fourth force called gravity, and while it's important on cosmological scales, for galaxy formation structure like this, the force is too small to be important on scales in which we're considering for a particle. So now let's go through the particle content of the standard model. Here we have, these are all the particles in the standard model, and we have a split such that the bosons are on the right. These are particles with integer spin, and on the left here we have the fermions, which have a spin 1/2. And amongst the fermions, these are also split into two categories. We have the quarks, and we have the leptons. Another bit of structure that's in the standard model here is we have 3 generations, where with each successive generation, these particles have higher and higher mass. Okay, so let's talk about the interactions occurring between these particles. So first, for the strong interaction, this is mediated by the gluon, and this interacts with only the quarks. We have the electromagnetic interaction, which interacts with anything that has electric charge. And lastly, we have the weak force, which interacts with all the fermions and the Higgs. And these are governed by the W and Z bosons. Okay, so what about the Higgs? The Higgs is one of the most important particles in the Standard Model. It's responsible for giving mass to all the particles and for what's called electroweak symmetry breaking. So at early times, the electromagnetic and the weak forces were actually unified into one force, which is known as the electroweak force. And by unified, I mean they act as the same force. But the Higgs will break the symmetry into the two forces we know today, the electricity and magnetism, and the weak force. So this is an example of symmetry breaking, and we'll see later on in my talk that we also need to break supersymmetry in order to use it in our as a theory that's experimentally relevant. Okay, so let's talk about the Higgs field. It's composed of two complex scalars, as in spin zero particles, and that corresponds to 4 real degrees of freedom. Down here on the right, we have this cartoon, which I've taken from quantumdiaries.org. It's actually a really good place to give introductory physics to the introductory explanations for the Higgs and other Standard Model processes. So I should definitely check it out. So what we have depicted here is the Higgs field in its potential, and at the 0 point where it is right now, it's an unstable equilibrium, and as the caption says, this costs too much energy. I think I'll hang out down here. So this process where the Higgs moves from the middle to the minimum of the potential, this is what spontaneously breaks electroweak symmetry. And let's go through that more on the next slide. And this is what's known as the Higgs mechanism. So just to go through in more detail, we have the electroweak force, which is composed of 4 bosons. We have 3 W's, 1 B. And what happens in the Higgs mechanism, the charge components of the Higgs fields will combine with the W1 and W2 bosons. And in a process which we say the W's eat the bosons, and by eating them, they gain mass. So this is the process which is giving them mass by this Pac-Man action here. We have, so that's for the charged bosons, and then for the neutral bosons, we have the W3 and the B, and they interact with one of the Higgs fields, one of the Higgs particles here, and this causes the Z to get mass, so it eats that particle, and we also have a mixing between the W3 and the B. That's why we have a shading, different shading for these two. So what this ends up giving us is the I should also mention that the photon does not eat a boson, so it remains massless. And the mixing gives us the electric charge that we know today. So this is the usual photon responsible for the electromagnetic force. So now there's one leftover degree of freedom, that's the Higgs boson. And it was discovered a little more than 2 years ago by the ATLAS and CMS collaborations, showing the ATLAS slide since we're an ATLAS university. The Higgs mass was found to be 125 GeV. And what we're showing here on the right is in particular, the Higgs channel to decay to 2 photons. And what we do is we combine the invariant mass of the photon pair, and we look at the background, which is in the dotted lines, and then in the solid line is the signal the background fit. We see we have an excess right there at 125 GeV. So that bump is what's coming from the Higgs decay to 2 photons. So this is one of the major components to the Higgs discovery. Another important aspect to the Higgs boson is that it couples to mass. And the more massive the particle, the stronger the coupling. So this is especially important for 3rd generation. And to remind you, the 3rd generation is the top and bottom quark, and the tau lepton and the tau neutrino. Okay, so this is great news. We found the Higgs. The Standard Model is complete, right? Well, there are theoretical problems that arise with having a fundamental scalar in your theory. So the Higgs can couple with virtual particles, well, and any particle in the standard model also does this. And these pop in like diagrams shown down here. This is a Feynman diagram where time goes to the right. And we see that we have a Higgs, which interacts with two virtual top quarks, and then they reannihilate to give us the Higgs back. So these virtual particles just pop out of the vacuum, and what are known as loop corrections to the mass. So normally this is not a problem. Standard model particles, you have these corrections that occur all the time. You just take them into account. But for the Higgs, because it's a fundamental scalar, these corrections go quadratically. And this turns out to be bad because of these virtual particles can carry any momentum ranging from 0 all the way up to the energy at which your theory breaks down, which we call the cutoff energy. Usually we take this energy to be what's known as the Planck scale. This is where gravitational interactions do become important. But this scale is at 10 to the 19 GeV, which is a lot. It's far removed from the weak scale, which is 100 GeV. So let's go through this equation here. So we measure the Higgs mass. That's the physical Higgs mass, and we find it to be 125 GeV. But that's really composed of some bare mass, which we can't measure, and corrections, which I've shown that should go quadratically and should be the order of the Planck scale. So this is an issue because this is a number that's 10 to the 19 GeV, and this is a number that's 100 GeV. So we would expect the Higgs to be about the weak scale because it's involved with electroweak symmetry breaking, gives masses to the W's and Z's, so it should be about the same. But what we don't expect is this very unnatural cancellation between the bare and cutoff masses to give us 125 GeV. So what this leads us to think is that there's some new physics that we're missing. So one solution to this would be let's consider the case where we have a partner to the top quark. Over here on the right, it has mass. It also interacts with the Higgs. Diagrams of that form. And when we go through the correction for the partner to the top, the corrections go quadratically, but with a positive sign. So it turns out that these quadratic corrections will cancel out. And I didn't go through this, but this partner, let's make it exactly the same as the top, the same mass, the same couplings, except let's give it a different spin. Let's give it spin 0. So effectively what we've done is we've created a connection between fermions and bosons. So fermions with half-integer spin, bosons with integer spin, and this is the basis of supersymmetry, that there's a symmetry between fermions and bosons. So if the world were exactly supersymmetric, we have all these particles popping up here, where for fermions, we get a partner for the left-handed and right-handed type. So let me go through what we call these particles in this theory. So the typical convention for partners of the fermion, we add an S to the front of the name, so a fermion will become a spermion. So we have partners of the quarks are the quarks, partners of the leptons are the sleptons, neutrinos, exactly. So that's for the fermions. For the gauge bosons, we add an eno at the end. So instead of the Higgs, we have the Higgs eno, photon, photino, and so on. But if supersymmetry were exactly, it was an exact symmetry, it held at low energies, we would expect to see these particles flying around. For example, a selectron, partner of the electron, is very light, it's charged, and we would find this spin 0 particle, but we don't see that. So therefore, we have to, if we want to use supersymmetry as a theory, somehow hide it. And we do that by breaking the symmetry, which... Mhm.
Why you have 3 different electrons?
So this is the electron, and this is the left-handed and right-handed selectron. Anything else? So, so what we do is we break the symmetry so that it's no longer held at low energies, and the result of this is that particles end up being at high mass. So we haven't detected them yet; they're out of reach for now. So we have standard model particles in here, and then supersymmetric particles up there. So for this talk, we're only going to focus on a few of the supersymmetric particles. Something else I should mention, this is the minimal extension to the standard model, which is called the MSSM for short. I might be using that. Keep that in mind. So we're interested in looking at the third generation spores, the stop and the sputum. We're interested in the Sleptons and the neutrinos, and also the neutralinos and the charginos. And what these are mixtures of the gauginos. These are the partners of the gauge boson. So the BiNo, the WiNo, and the Higgsino mixed together to give us 4 charge neutral states and 2 charged states. So an important aspect of supersymmetry that we usually impose is called our parity. And if we assume that our parity is conserved, it gives us some important consequences. For example, the lightest supersymmetric particle ends up being stable. So this is important because all heavier supersymmetric particles will decay down to the LSP. So at colliders, if we produce these heavier supersymmetric particles that decay down, and the LSP will end up escaping the detector, resulting in missing energy. It also has cosmological implications because it's weakly interacting and has mass. It works out that it's a good dark matter candidate, and that it's stable. In this talk and in my work, I have used the lightest neutralino as the LSP. So this will pop up throughout the talk with this symbol chi sub 1. So let's talk a bit more about the chargino and neutralino sector. We have 3 different scenarios that can occur, which give a different composition of the LSP. So here we have the BiNo, WiNo, and Higgsino, and they're each governed by different mass parameters M1, M2, and mu. For the BiNo case, only one particle is governed by M1, so we end up only with 1 LSP, which is mostly BiNo. In the WiNo case, we have 2 particles governed by M2, so we'll end up with a LSP. So that's the lightest neutralino here. And also at slightly higher energies is a light chargino. And then for the Higgsino case, we even add an additional neutral state. So throughout this talk, I'll discuss which particular scenario I'm using in my project, which I'm talking about. Yes?
All right, what do you mean by governed by?
These are the breaking masses. So when you break supersymmetry, you have to add mass terms, and these correspond to the BiNo, WiNo, and Higgsino states. So M1, M2, and mu. Okay. All right, so let's continue. So how might we look for these things at the LHC? We do it the only way that a high-energy particle physicists know how. We collide 2 protons together and see what happens. So in this process, and we collide these at very high energies, out of which can spit out potentially supersymmetric particles. So here we have the pair-producing selectrons, and then these selectrons can further decay down to the LSP and electrons. So the signal that we'd look for in this case would be 2 leptons plus missing energy. So as a phenomenologist, what I do is I act as the interface between theory and experiment. For example, if ATLAS results show something interesting, we can try to interpret those results by using some theories. So we try to explain what that excess is. On the other hand, we can use pre-existing theories to predict what you might see at colliders. So where the phenomenologists act as the mediator between the two. But we're still more theorists than experimentalists. So when we work with data, we end up generating it ourselves by using Monte Carlo. So for example, so the way this process works is we have some process that we want to look for at the LHC, let's say. And we determine what the potential standard model backgrounds would be to this process. So then we generate both signal and background events using an event generator. And by event, I just mean a readout of momentums, energies, positions of all these particles. But this is far too much information. We don't get that much from a detector, so we have to pass it through a detector simulation to make the data more realistic. And then from that data, we generate histograms of specific kinematic variables, which we're interested in looking at. So what I've shown here is missing energy, where the solid histograms are the background and the dotted ones are the signal. And by looking at these histograms, we try to identify regions in which the signal is more important, or it dominates over the background. So we isolate those regions, and then we want to determine whether or not the significance is, this excess signal that we have in these regions is significant. And then we make significance plots and exclusion plots. So what types of things can we detect in the detector? So here I'm showing a schematic of the Atlas detector where this is the interaction point, and the beam is actually going into the cage. And then this is the detector shells going radially outward. So we can detect charge states, like the proton and the electron. And these are light, so they get detected in the electromagnetic calorimeter. Looking like what's called jets. That's how we detect those types of particles. Muons, because they're heavier, will actually penetrate through the electromagnetic calorimeter, and we detect them further outside the muon calorimeter, muon spectrometer. And lastly, we have particles that we don't actually see. These being, in the standard model, we have the neutrino, which interacts weakly with the text, and the same goes for supersymmetric particles like the neutralino. So the signal that occurs out of these would be missing energy. We expect energy to be conserved, so when we see that there's more energy going, so more momentum going in one way, we can assume that there's something missing. So that is how we detect those particles indirectly.
So for electron and photons, one is a solid line with the other.
Oh, down here. So I didn't mention this. This is the tracker, and there's a strong magnetic field in there. So only things with charge is detected. So we see the electron, the muon, and the proton are detected, but the photon has no charge. So now this is a mess, but it's this is the current results for supersymmetry at the Atlas experiment. In particular, you notice that these are exclusion limits, masses being pushed up to about 1 TeV for a lot of theories. But you notice there's some white space in here, and this is actually the region where I've done my work. In regions, well, so this is the third generation quark sector, where the backgrounds are very high, so it ends up that these particles are very hard to detect. And on the other hand, we have the electroweak sector with Sleptons and the charginos and neutralinos, and these are weakly produced. So these are hard to produce, so we don't see them, and these are hard to find, but easy to produce. So let's first talk about Slepton projects that I worked on. So we looked at Slepton production in 2 ways. we have the usual just pair production, which then further decays down to lepton and LSP. On the other hand, we can produce them by other heavier supersymmetric particles, and then they end up popping in cascade decay. So here we have, say, the neutralino channel decays to a lepton and a slepton. The slepton then decays to another lepton and the LSP. So let's first talk about the cascade decay project. This is a project I worked on with Shufang and a collaborator from Irvine, Will Shepard. And our work was published in JHEP about 2 years ago. In this project, we consider a scenario that follows. We have a Vino-like LSP, and we have two Vino-like neutralino and chargino. As I showed you on the previous slide, we produce these particles, which then decay through intermediate leptons, and then ending up decaying to the LSP. So what we end up using, if we take a look at this one half of the decay chain, we have this decay topology shown here. And if we take the invariant mass of the lepton pair, these two particles, two leptons sticking out, we end up finding a very distinctive kinematic feature popping up in the dilepton invariant mass. And that's a triangle shown here. And the important part about this is that it gives you a distinct cutoff in which you can really look to. It's a very distinctive feature to pop up over background, looking for this sharp cutoff. And we can determine, so from this cutoff, it puts constraints on the masses of the mother, intermediate, and daughter particles in this decay chain. So what we try to do is we consider a 3-lepton signal. We produce signal from the standard model coming from 3 leptons, and we've also superimposed signal from our supersymmetric process that we're interested in. And on the right, you can see we can distinguish the cutoff at high energies, where the standard model background is relatively low. Whereas if we move closer to this region here, where the Z resonance is, the Z boson, we see that it's very difficult to identify where a cutoff is, or if it's even there at all. So this is just to show you that this procedure works well, but only in areas where you don't have huge backgrounds, like in the Z region. Okay, so we run Monte Carlo and we scan over the parameter space. And we first try to identify how detectable the signal would be. So on the left, here I have the cutoff mass versus the effective cross section of a theory. So this is effectively the amount of signal you would get from a theory, and what we're showing is the amount of signal required to have a 5 sigma detection just by using this this method of looking for a kinematic cutoff. And we see that in regions near the Z, it becomes difficult to detect this because of the high backgrounds and the ambiguity of where a cutoff might exist. Whereas at high energies, it becomes relatively easy, so the amount of signal required is less. Okay. And I want to stress that what we've done here is we've done it in a model-independent way, where in any theory where you have a decay topology, as I showed before, you will result, you can use this method in order to try to find what you're looking for. So it doesn't have to be supersymmetry, it can be extra dimensions, it can be whatever you want. So this is very flexible, this method. On the right-hand side, we apply a model of the MSSM, where we're showing the amount of luminosity or amount of data required to detect this signal with 5 sigma significance. So I'm showing plots in the space of lepton mass versus neutralino and chargino mass. And I've added on the dotted lines for 20 inverse Tempter barns and 100 inverse femtobarns at the 14 eV LHC. So we see that using just 20 inverse femtobarns, we'd be able to discover leptons and the charginos with this method. Masses of the lepton up to 500 and the neutrino up to about 600, 650 TeV. So now let's move on to the pair production process. This is a project worked on with the same collaborators and also with Michael Ramsey-Musoff, who's a professor at Amherst College. This is a paper we expect to submit sometime next week. That's exciting. So here, what we want to do is look at different types of LSPs and see how that might have changed the current limits on Slepton pair production. So in this case, we're considering all three of these scenarios where, because the LSP is governed by its lowest mass parameter in each case, you end up getting more and more particles in the Wino and Higgsino case, allowing for more decay channels. And this is what we're going to try to utilize. So in the usual pair production, you just have Sleptons going to leptons and LSP. But what if we add a Wino or Higgsino in the mix? This decay can now go through a chargino. So what results is that now we can generalize this pair production to include neutrinos. And the ultimate goal of this is that we still want to recover a 2-lepton signal so that we can relate it to what experiments are currently looking for. So now with this bottom leg, I've added a neutrino, but it goes through a chargino such that we end up with a charged lepton here. So that's important. And another important thing to note is that because the masses of the chargino and the LSP are very close together, the resulting products coming from this decay, when this eventually decays down to the LSP, will be soft. So, and so soft that it won't be detected by the Atlas detector. So in this sense, this diagram is effectively the same as the previous one. We're still recovering 2 leptons plus missing energy. So now the current issue. So on the one hand, we've added additional production mechanisms which increase the signal process, but we've also we're now limited by the in particular, it becomes interesting in the Higgsino LSP scenario. And the Higgsino couples the same way as the Higgs. It couples to mass. And the lightest leptons are very light, so they couple very weakly to the Higgs. And because of this, the Higgsino contribution of the LSP is actually not the dominating factor in determining the couplings. It's actually governed by small Wino and Vino contributions in the LSP. So remember again that all these particles mix together, and while they're dominantly one particle, they have little bits of each of them mixed in. So what I've shown here is the decay with the decay of this lepton to charged leptons and neutrinos. Sorry, neutrinos. And we end up, in this case, that there's a cancellation in the process, which is popping in over here on this diagram on the left, where we have the follow the blue curve, and we see it as a minimum right here around 1/3, where this parameter is the ratio of the Vino and Wino masses covering the particles. So with the Higgsino LSP, we actually have a wide range of possibilities that, of possibilities. So we could have a worst case where we're really not going to decay through leptons. We're going to prefer to go through neutrinos, which will not add to our signal. Whereas in other cases, we're doing pretty good, and it's almost it's about 90%. So what we've done is we've we do Monte Carlo, and we try to match what the experimentalists did for the 2 lepton study for Sleptons. So that is the blue and yellow or orangish curve. And what we have here is we find that we can reproduce that quite well. So effectively we match their exclusion limits here. And then we expand to other types of LSPs. So in the case of the Wino, we increase the effective limits because we now have additional production mechanism, so we increase the signal. And then in the Higgsino case, we actually have a wide range, ranging from the worst case to the best case, depending on the branching fraction to leptons. So that's in the LSP and Slepton plane. So we see we can even, in the case for the best case, Higgsino case, we can really rule out almost up to 500 GeV in the best case scenario with that Higgsino LSP. And on the right, we're showing sort of a translation of this plot, which has the branching fraction built in as a function of N1 and N2. So we're putting N1 and N2 on this axis and the lepton mass on the x to show how, depending on what those parameters are, what the exclusion looks like in that parameter space. So let's look at the red curve, the solid red curve. We see that regions down here are excluded, as well as regions above this other red curve, but we're insensitive to regions in between, and that's because of this minimum that's popping up down here at about 1/3 of this M1 over M2 parameter. It turns out if you just flip the sign on this M1, M2, that you end up, you can really, you can dominantly decay to lepton states. So this actually just pushes the limits up very high. So that ends up corresponding to the best case. So that was for 8 TeV using the current results. We also then expand this to 14 TeV, look at the next run of the LHC. And what I'm showing here is the 5 sigma discovery reach in the LSP mass and Slepton mass plane. And we see that in the best case for the Higgsino type LSP, with 100 inverse femtofards of data, we can discover Sleptons all the way up to 800 GeV. Yes? So here we're plotting exclusion, yeah. and here we're plotting discovery. Keep that in mind.
Okay. So most of this already excluded.
Sorry?
Most of this already excluded.
So it depends on what. Well, it depends on what the. Yes, you're right. So really, what we could do is overlay the. So, but it's a bit complicated because it depends on what state it is. So for the Higgsino, we could discover up to 800, but right, it's excluded currently at 500. Good point. Yes.
This is still using the same base selection.
Yeah. So yeah, using MT2 kinetic variable, 2 leptons with missing energy. Let's see that. Mm-hmm. Okay. All right, so now let's move on to the STOP project.
John?
Yes.
So the discovery is at 5 sigma, right?
Yes.
And the exclusion is at 2 sigma.
Yes, that's right.
So those got to.
Yeah, but this one is at, well, that's right. What we're showing here is the discovery at 14 TeV. I also have plots for exclusion, expected exclusion at 14 TeV, and those are pushed up a little bit high. So I believe that's okay. So moving on to the Stop and Spot project. This I worked on with Chufang and Huan Yan. And this paper we're hoping to submit later this month. In this paper, what we want to do is expand upon what current experimental searches are doing. Primarily, they look for signals of TT bar and missing energy for the signals resulting from the stops. And what we want to do is highlight other important decay channels which can be dominant in certain parameter spaces. And this will help both to cut that background and will change what the current limits could be, depending on what these parameters are. So we head back to the Higgs. So the stop and the Higgs are tightly coupled, again, due to these strong Yukawa couplings. The couplings are proportional to mass. And because of that strong coupling, the terms that pop up here for mass corrections to the Higgs are actually the dominant terms for the Higgs mass correction. So think of it this way. We discovered what the Higgs is. It's that the Higgs mass is 125 GeV. So that puts constraints on the on stop masses and stop parameter space because of this form of correction. So that some stops pop in this formula. If we expect these corrections to be of a natural form, and if we're using supersymmetry, we expect that it should be natural. That's sort of our motivation for doing that. This puts mass of the stop. It can't really be any higher than 1 TeV. So we expect, if stops exist, then we should be able to see them at the LHC. This is the status of the current experimental searches. On the left, we have the stop exclusion. The current exclusion for the stops, and on the right, for the bottoms. And in each case, we see that for a massless LSP, we can exclude stops and bottoms of up to 650 GeV. Now, the caveat with these plots is that they're only using the decay channel to top LSP. As I'll show in many different cases, that this branching fraction is not 100%. So you end up by suppressing this background, this branching fraction, you end up pushing these limits back because you can't say as much about it. So in particular, so we look at a variety of different scenarios, but for the sake of time, I'm only going to talk about one. We consider a simplified model in the MSSM where we only consider one stop and bottom. So the other two stops and bottoms are decoupled at high energies, as well as the rest of supersymmetric particles. We have these stops. We give them the opportunity to decay through intermediate neutralino and charginos, and these are Reno-like, and also the Veno-like LSP. So the importance of having intermediate decay channels is that we can have additional decay products popping in. So in particular, for the neutralino state, you can decay through a Z or a Higgs on the way to the LSP. This is going to add additional signal that we can look for. Okay. So now let's go through what these branching fractions exist. So what I'm showing is the branching fraction as a function of stop and bottom mass on the right. And we see that the decay through the intermediate particles is actually dominant. So in particular, I want to highlight the neutralino channel again. It pops in at about 30%. Yes.
So this is with what are your ratios? Stop charging with usually the mass ratio. It's all a hierarchy.
Yeah. So we consider I think a 300 mass intermediate neutralino chargino with 100 GeV. Yeah, so that's why you're seeing some turning on of these states here. So that's just when decay is kinematically open.
So it's fixed 300.
Sorry.
The chargino mass is in a fixed ratio of the stop mass. It's just fixed at 300 joules.
We use, I believe the mass difference between, these plots have the mass difference to be 200 GeV, but in our later work we actually use 150 GeV to be the splitting. Yes, so to fix the splitting and we'll scale through that. So that's for the left-handed stops and bottoms. So in the right-handed case, we only have one. We have the stop. And we see that this is dominant pays directly to the LSP in the top. So, and what you could think of with this plot is that what current Atlas searches are doing is they're looking for cases with a right-handed stop in this scenario. That's one way to interpret those results. Okay, so again, what we're going to do is run Monte Carlo simulations. We're going to take advantage of this neutrino K, which will end up giving us a Higgs. So I don't want to go through all this diagram, but the big things to take out of this are that, well, we're having the Higgs go into these because it has a high branching ratio, so we don't run into suppressions there. Our signal is actually 4 V jets, 2 additional jets, and 1 lepton. And major backgrounds coming from this are from TT bar, and that's sort of what's the not highlighted part. So these other 2 legs of the decay actually end up looking a lot like TT bar. So that is a big background in this search. So what we do is we scan over parameter space, and we're showing discovery reach and the exclusion in the LSP and stop and bottom plane here. So for zero mass LSP, we see that we can optimistically discover stops masses up to 650 GeV. Pessimistically, we'll be able to exclude them up to 800 GeV. And very similar for this bottom. These are plots from 1 minute.
Under FMR 14 tab.
Oh yeah, I was missing that. Sorry, thanks. This is yeah, in the next run of the LHC, 14 TeV of center mass energy, 100 inverse vector quantity. So now let me conclude. I've shown to you that supersymmetry provides a way to solve the hierarchy problem, and I've shown you a few ways in which I've shown you a few places where supersymmetry could be hiding in the Slepton sector or in the stop sector. And in particular, we can look for Sleptons using cascade decay, utilizing this kinematic triangle, and then it can be applied to models other than supersymmetry. We can also look at direct production of Sleptons and just expand upon what current experiments do by looking at different LSPs. So we have a wide interpretation of what these results could give us. And for the stop sector, I've shown that by looking at new decays, we can identify regions where decay is not the dominant direct decay through LSP top, and conclusions from there. So with that, I want to thank a few people. I want to thank my advisor, Shu Fang, thank Huan Yan, and the local Atlas group has been a lot of help. And lastly, thank my friends and family for their continued support. And with that, I'll take any questions.
No? Good. Good.
You said the natural mass for the S bottom is 1 TeV.
Well, for the stop. So the stop couples more strongly to the Higgs, so we have better constraints on what that's. But the bottom should be nearby.
Is that what stops all these things? They can't all the supersymmetric particles can't be insanely heavy.
Well, yeah, because the Higgs would couple to them, and then we'd have corrections to that, and then we'd end up with another unnatural problem, where if we have heavy particles, the math is going to be corrections from them, which would try to push the Higgs up, but we know it's at weak scales, so in order to keep it natural, we really should be at low mass systems, like TeV. low mass is extremely right? Yes.
My impression is that, well, I guess you showed a plot that said there's many different sectors to plug into for supersymmetry. And, I don't really understand why you collaborate with this one particular sector to work in versus many others.
Well, our motivation was that the current results in these sectors are, so the limits are relatively weak. So there's still work to be done to try to find sample Sleptons, because they're weakly produced, they're harder to produce and they're harder to find. Stops are easier to produce, but they're harder to find because of the heavy backgrounds coming from the others. So this was the motivation for looking in these two regions, as well as the stop connection to the Higgs.
In terms of like promising areas to be looking right now.
Well, with those other limits, I mean, we've excluded like the first and second generation quarks up to TeV and maybe a little beyond. So strongly produced particles are not there. They have to be at a high mass if they exist at all. So currently they're not accessible. They might be accessible with 14 TeV energies, but this is these are things that are accessible in the mass range, but it's still weakly produced, so it's hard to see them or hidden by background.
Comment about your very last question. I think it's useful to recast the current distribution in the stops.
Yes, that's actually something we want to do. It just wasn't in time for this defense.
Yes, I think finding yes, it's like it is regular.
Yeah, I think what approximately it's somewhere
It's not in this chart. It was
about 500.
Yeah. And the squadron search after the limits become one. Because the squadron was actually due to specificity and the extent of its less than 1%. So the squadron is almost less than
Also, in your last one, you said you're looking at that big decay chain. How did you use that? You said you were using that on the other hand.
Yeah, so you have additional B-jets going to help cut the background.
Just the B-jet code?
That's one part. We stop decays. Let me bring it back up. In this big decay chain, you're also going to have a lot of jets being produced, so we can use an HT cut on jets, try to cut down on TT bar as well. So just by having more stuff, you can cut on things having more decay products. It wasn't implemented in this, but that would be something to look into. Try to reconstruct the Higgs as an identifier. Yes.
So, how do you propagate your AT?
We just regenerate signal and backgrounds through the Monte-Carlo process showed before.
You said a lot of the particles that you're looking for are within the accessible mass range at the other stage, but they're just hidden by background, possibly.
Well, the stops especially are hidden by background. The electroweak particles are produced weakly, so you don't produce as many.
Okay. So do you have estimates for all those particles for like how high of luminosity you would need?
Well, that's effectively what I showed. At the amount was. So here, what we're showing is parameter space which is accessible given 100 inverse femtobarns, which is sort of a benchmark.
Right. But eventually LHC will have a higher cross section.
Yeah, so we can. We've also made these plots for 300 inverse femtobarns, but that's further down the line. So yeah, so you just keep extending these things. But the problem with that is at some point it becomes unnatural for the stop to be too heavy.
these objects not the weak on masses?
Right. So I haven't said anything about that low mass area. Different backgrounds to deal with in there. So you're right. So it isn't all the way down. There's a stopping point here at 350 GeV. So anything below that, we don't have sensitivity.
At 14 dB, you're going to have a much more brighter flame.
Yes. So that'll be a big issue for the stop paper. But luckily, in the Slepton case, we imposed jet veto. We don't have to worry about pylon.
I guess just to finish my question, what year do you expect, based on the LHC projections, to be able to get up to like 1 TeV?
Actually don't. When is the LHC turn back on? 2 years?
Next spring.
Oh man! Wow.
March. The next spring it will be turned on. Thinking how the how we call it, the running period. It will accumulate 100 and then we're going to shut down again for an upgrade. Then we run free period. Then we will run until
Okay.
and then we will accumulate 300 units.
But in the run 2, it looks like you can't exclude everything that you need to. Or you don't have enough data to say for sure, like we haven't found anything.
Yeah, if you want to go all the way up to 1 we will do more than 100.
Actually, that's going to be years.
For someone else's PhD.
So you can still probably alive. Okay, if no other questions, thanks everybody for coming today.